Okay, so for the number systems, I would like to introduce you to the first very conversion system, that is from the binary system to, I mean, both to the decimal. Now, many of us have this idea that, when we have a binary system or when we have a decimal system, why go for a binary system? It doesn't make any sense. But it does make any sense because binary system helps us represents only two values, that is 0 and 1. So when you're representing only two values, that is 0 and 1, 0 corresponds to 5 volts DC. Now friends, I am not going into the current market scenario of 3.3 volts and 1.2 volts, even some microcontroller core runs at 1.8 volts. Forget about all these things. Just concentrate on 5 volts and 0 volts, right? Plus 5, minus 5, plus 12, minus 12, and 0. This is going to be your concept, right? So 0 can in some cases correspond to 5 volt DC. In some cases it can also correspond to 0 volt DC. Okay, it all depends on the type of logic, because when we are saying that 0 means a 5 volt DC, we are sort of referring to a negative voltage logic. Many of you must have heard of a negative voltage logic level. So this is nothing but a negative voltage logic level, right? So you can call this, I'll use a different ink for your benefit. This is called a negative voltage logic, right? And in some cases where 0 volt is corresponding to minus 5 volt DC, 0 volt DC, it is called a normal, you can say, ground. That is, you must have heard of it. Now what is this one for? One is for a 5 volt DC or a 0 volt DC. Then the logic level just simply reverses, because 1 equals to 0 volt DC will be a negative logic level, and this will be very definitive for you, because you will see many ICs. You will see, I am telling you, you will see many ICs that have a box and a dot over here. What the hell does this mean? Have you ever wondered? It means this. It means that this IC, you will have something called a chip enable or a serial enable or a system enable, anything, I don't care. So this will basically give you the idea that your IC or your chip will start working when you provide a 0 volt DC to this particular pin. Nobody will tell you this. Nobody will tell you this. So you must know that a 0 volt DC as a logic 1 is to be applied over here for enabling the chip, right? So this will cover up in many other topics, so you need not worry. Shit, I think I used a permanent marker. Anyways, let it be, doesn't matter. So now, what is the solution to this particular system, right? So I'm going to discuss the binary system to the decimal system, 0 volt, 5 volt conversion. So how do you convert a binary logic level to a decimal logic level, right? In binary system, the first position is 2 to the power 0. Why is it 2 to the power 0? Because any number system that starts with a power of 0, that is 1, that is unit. It's a unary position. So the starting level would be 2 to the power 0, then it will be 2 to the power of 1, then it will be 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, and it can go on to 2 to the power of n. I hope you can see it. So this is the normal binary level of conversion. So if you want to convert a binary number into a decimal number, like shown over here, then you must multiply the value. There are two things that you must remember. One is the place value and the actual value. The place value will basically give you the value of the unit. I got some weird restart request. Okay, so the place value will give you the value of the particular unit at that particular position. So 2 to the power 0 over here means equals to 1. The 2 to the power 1 over here equals to 2. I write it for you. The 2 to the power 0 is 1 over here. This is equals to 2. This is equals to 4. This is equals to 8. This is equals to 16. This is equals to 32. And this is equals to 2 to the power n. I can't write any value over here because I do not know the value of the n. So if you study properly, you will understand that 2 to the power of any number is basically getting multiplied over here, right? So the actual value is nothing but the presence or the absence of this particular number in your decimal system. That is, whether 2 to the power 0 is there in your decimal number. If it is not there in your decimal number, it doesn't make any sense. You're just going to shun it off. So I give you a decimal number, say I'll only go up to 2 to the power 5, right? I'll say 1, 0, 0, 1, 1 and 1. Here you will see that 2 to the power 0, that is 1, is present over here. So 2 to the power 0, that is 1, is required in your decimal number, right? 2 to the power 1, that is 2, is required in your decimal number, that is 2. 2 to the power 2, that is 4, is required in your decimal number, and that is 1. So this is also 1, but this is 0, means that this is not required. It's not required for your decimal number. That means your binary number doesn't have the decimal equivalent or decimal equivalence of that particular number. It's like a person who is totally absent in your class. So you need not have that particular person in your play group, right? So what I will do is I will simply remove 2 to the power 3, that is 8, is not required as 0. 2 to the power 4, 16, is not required as 0. But 2 to the power 16, that is 32, is there. So that is required. So you have it, that is as 1. Now you multiply the position or the place value of each and every actual value. That is, if 2 to the power 0 is present in your decimal system, then you must give its presence over there. It's like if a boy is present in your class, you must tick him as present in your attendance register, right? So what I will do, I'll just multiply this by 2 to the power 0 is 1, so I just multiply it by 1. 2, I multiply this as 2. I multiply this as 4. I multiply this as 5. So your entire number will basically become 5 plus 4 plus 4 plus 2 plus 1. That comes to 5 plus 4, 9, 9 plus 2, 11, 11 and 1, 12. So your number, which was basically, if you have a look, which was basically 1011, is nothing but 12 in your decimal. So this is your decimal number. Right? So now that was from binary to decimal. Now you will ask me that, okay sir, you had a small number and you converted it into a decimal number. What about a huge number, say 2 to the power of 35 or 2 to the power of 8 or 2 to the power of 10? it basically doesn't make any difference, it doesn't make it basically doesn't make any difference if you are converting any big number. You just you know you just keep multiplying, that particular number and the place value and the actual value, that is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, 2 to the power of 7, 2 to the power of 8, 2 to the power of 9, 2 to the power of 10, 2 to the power of 11, 2 to the power of 12, 2 to the power of 13, 2 to the power of 14, 2 to the power of 15. I took up to 15 because usually people are very worried with 16-bit numbers. I have, you know, I just shared a very interesting topic with you. That is, I had a group of students who were working on a project, and they had to deal with 16-bit binary numbers which were not BCD, that is binary coded decimal. I haven't discussed BCD over here. I will do it, but they were really worried about that, and they told me that, sir, how will I handle with a number that is 2 to the power of 16? I mean, I don't know how to describe it to you. It's huge. So I just told them, keep on multiplying. 2 to the power of 10 is 1024. That's a fixed value. So keep on multiplying. 2 to the power 11 is 1024 into 2, that is 2048. 2 to the 2 to the power of 2 to the power of 12 is double of 2048, that is 4098. 2 to the power of 13 is double of 2048, that is 4096. Then it is double of 4096, and you can reach the particular number. So that's the rule. That's simply the rule. Just got you have to have a calculator, and you just gotta multiply. If you have a binary number like this, like I'm going to give you right now, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 0, right? So you're just going to multiply each and every. I'm going to give you 5 minutes, not 5 minutes, I'm going to give you 3 minutes of time. Now it is the recording time is 18:57. So I'm going to give you, say, 5 minutes. I'll be back after 5 minutes, and I want you to solve this particular problem as I told you, by multiplying the place value. As I said, that they have this is the place value, and this is the actual value. So you're going to just simply multiply the place value by the actual value, add it up, and find the decimal number. I'm going to come back after 5 minutes, and I want the answer correct, because it's not an interactive session. I can't see you, neither can you see me. It's only through a video. So I will give the solution over here, but I hope that it matches yours. So bingo, best of luck, you'll do it. Okay, so I will provide the solution to the problem. First of all, I will erase the 2 to the power zeros because they are of no use. So first you remove this one, you remove these two, you remove this one, you remove this one, and remove this one, right? So that eases your problem, right? So now what you do is you just multiply it by 2 to the power 1, that is 2, 2 to the power 2, that is 4, 8, 2 to the power 6 is 12. I hope it is 12. I'm not doing it wrong. Let me use the calculator. No, let's not take chances. Okay, so this comes to 64. This comes to 64, right? Then it is 2 to the power 9. So it's 6. I'll multiply it with uh, 8 and 9. That gives me 256 into 2, 512. So 2 to the power 12. God. That's 4096, right? This is 8192. This is going to be I'll tell you how much it will be. 16,384, and this is going to be, this is a famous value, 32,767. So if you add all these values, you will get the decimal equivalent of your binary number, right? So what I want to say is, to convert a number to a binary, what you just need to do is multiply by the actual value with the place value and you get the number. There's one more thing that I want to discuss with you before closing this session. I don't think I'll be able to discuss the decimal to binary over here because that's a big session. I'll do it in the next one. But sometimes what happens is, you have a binary coded decimal. This is very important. This is very simple. There's nothing to worry. If you can handle this, you can handle this. This is nothing but, it's a set of 4 binary numbers. It is just simply a set of 4 binary numbers, or maybe more. Say 1011 0101 1110, right? So what you're going to do, you're going to apply the same rule, right? So this is going to be 2 to the power 0, so that's 1. This is going to be nothing, so you just can erase off. This is going to be 2 to the power of 0 1 2, so that's 2. And this is going to be 2 to the power 0 1 2 3, so that's 4. So this totally gives you how much? 10 in decimals, right? 101101. I hope I'm doing it right. 1101, this is 2 to the power 0, that's 1. This is nothing. This is 0 1 2, that's 4. 0 1, sorry, oh, I'm sorry, I'm so sorry, I'm so sorry. This is 2 to the power of 0, that is 1. This is 2 to the power of 2, that is 4. And this is 2 to the power of 3, that's 8. So it's 8 and 4, 1101, that is 13. That's why I was thinking something was wrong. So this is 13 in decimals. Now 13 in decimals is the value for 1101. We have 1010. This is nothing but, you just don't need to bother about this. It's 0. 2 to the power 0. Here the place value is 2 to the power of 1, that is 2. So 2 multiplied by 1 is 2. Plus you don't need to bother, so it's 0. And 2 to the power 1 over here is 8. So the total value is 10. And over here, you don't need to bother about this. This is 0. This is 2 to the power of 1, that is 2. 2 to the power of 2, that is 4. And there is 2 to the power of 3, that's 8. So that's 8 plus 4, 12. And 12 plus 2 is 14. So 1110 is nothing but 14 in decimals. So this is nothing but a binary coded decimal. I'll just give you a binary coded decimal over here. Binary coded decimal is nothing. I'm just telling you. You know, it's very much required for displaying in the LED systems, where you see, you know, in the platforms or wherever you see a 7 segment display, you'll understand that the binary coded decimal is in use because a binary coded decimal will only be used in places where you cannot go above 9, because 0000 will give you 0, 0001 will give you 1, 0010 will give you 2, 0011 will give you 3, 00 I'm sorry 0100 will give you 4. And so if you carry on like this, 1001 will give you 9. And these are all the numbers that are required for a 7-segment display. So a binary coded decimal will never come into picture unless and until you have something to do with an LCD or a 7-segment display, right? So I close my session over here. If you have any questions, do write into my email address. That is, you have my email address, turjasusworld.in, right? You can put in over here. You have a chat facility in my website, but I would rather prefer not to use this because I'm very infrequent in chat, right? You can access me in Facebook. Just go to Facebook and just search for Turjasu. There's only one idiot who is there. So anything over here which you didn't understand, how to convert a binary system into a decimal system, I explained everything. Tomorrow morning, right? You know, tomorrow morning, it's pretty, actually I'm staying in India. I'm staying in Calcutta. So it's around, I think, it's around 1 o'clock in the night, so I'm pretty sleepy. I just wanted you to get through this thing, so I wanted you to get through this particular tutorial. Tomorrow morning, I'll be going through the decimal to binary conversion and decimal to hexadecimal conversion and hexadecimal to decimal conversion. So once all the conversions are over, we can really move into something that is fruitful, that is, we can really design into a microcontroller. Because unless and until you are well conversant with these conversions, you really cannot understand the softwares. I know it is a problem and I don't want you to face it because I faced it a lot. So I hope you've understood a lot and you understood my tutorial a bit. And if in case if you like it, just give it a like in my YouTube channel. Just subscribe to my YouTube channel. I'll be giving you free projects. I'll be giving you free free circuit ideas. Even you can, even you can just mail me some new project ideas. I'll be very happy to design them free of cost. Free of cost, I'll tell you, free of cost. And and uh, and what and what I mean, for embedded people, for people who love embedded electronics, it's going to be a plethora of a lot of things. So don't get disheartened. I'm a bit late. I'm going through some personal problems, but I'll be there and I'll teach you. Bye and good night.